Okay. Just got to check since we have new folks. Everyone, have you logged into Buzz? Do you know how to log into Buzz if you're new? Just to make sure everyone has access to it. I know we checked that last week, but at least one of our new people was absent last week, and I think I emailed the login information to them. So just making sure if you have any problems, let me know now before we get started, because I want you to be able to access all this. Don't want to forget about it. Got our first assignments this week, all that good stuff. Okay. All right, 16 of us. That's good. We're only missing 5 at the moment. Hopefully they'll be in here any moment. So. Anyway, so this week we're starting our usual virtual schedule. You have all your classes yesterday and today. The next 2 days are like optional days, which means your teachers will be here. I'll have a class meet on Thursday morning. And if you're having any trouble with this week's assignment, you can pop into class. Say, hey, Mr. Brock, yeah, I just finished my breakfast. I had some questions about this assignment. Not great. And then once I answer questions, you can go, because right now nobody's grade is below 70%. When your grade's below 70%, then you're required to come on Thursday, and you can't just leave. You got to stay in there and get work and get your grade up. So this week, though, nobody's grades below 70% because we haven't had any grades yet. So it's optional. If you need help with this week's assignment, come on by and see me Thursday. Friday, of course, there's no meets in any class. That's an in-person day. You can come up. We have a lab on the back side of this wall, and there's a room right over there. So that starts this week as well. But we're going to take notes today. We're going to do some algebra today. So if you get your pencil and paper ready, we're going to jump into this. We'll put it up on the screen, and we've got our first lesson of the semester. So for your new folks, we'll give you an experience and show you how this works. All right, this is our first lesson. Let's go to our grade screen. There's not going to be much on the grade screen. You can go with this icon, or you can go up here in the menu bar, but I'm going to just click on the icon. It's quicker. This will show all of our assignments coming up. If we had already done some, it would have, when you submitted it, what your score was, all that good stuff. But right now, we don't have any grades, any scores, but we can see the due dates. So we can see this week, we're just doing one lesson, exponential functions. Next week, we'll do logarithmic functions, and we have the little quiz, the mid-module check. So that is not a lesson. That's just a little quiz over the first 2 lessons. So that'll be due next week. And the week after that, we'll do graphing of both kinds of functions. And then we'll be up to the test here real quick. So January 18th, exponential functions. That's what we're looking at today. Let's go back to the activity screen, because that's where all the action is. Let's click this little arrow and open this folder. So here we can see all the way down to the practice test and the part 1 and part 2 exam. We have the 5.01 lesson followed by the 5.01 assignment. This is what we saw on the grade screen was the assignment. So let's go through the lesson this morning. We'll take some notes and see what we learn about exponential function. Starting out, I want to switch to our note screen right off. I have 2 different functions written on our notes here. So you can see we've got f of x equals 3 to the power of x, and we have f of x equals x to the power of 3. So kind of a reverse of each other. These both have exponents, right? The exponent is the x, the exponent is the 3. But when we talk about exponential functions, write that on our notes. Exponential function. This is an exponential function. This is not an exponential function. In order for something to be called an exponential function, the variable must be in the exponent. This is just a function that has exponents, but it's not an exponential function because the variable's right here. when the variable is in the exponent, that is an exponential function. So when we talk about exponential functions, it's important to understand what are we talking about. What is an exponential function? Any function that has the variable in the exponent, exponential function. And that's the first thing we're going to see in our lesson right here, once we get started on it. But this is talking about, have you ever watched a ball thrown high in the air? I'm talking about throw a ball straight up in the air. When it reaches its highest point, it seems to just float there for a second. It stops going up. It's not started back down yet. There's just a brief moment that it just sitting there in the middle of the air, which is pretty cool. If you haven't seen that, try that. At the top of the ball slide, it reaches a point that has 0 vertical velocity. So now we're talking a little science up here, some physics, right? The ball stops, and then it starts falling back to earth. And you can notice as it starts falling back to earth, first it starts real slow, and then it gets faster and faster and faster. The velocity is changing exponentially. It's getting exponentially faster. So what we're going to learn today is, how is an exponential function created? How can the properties of exponents, and we're going to write down the notes reviewing the properties of exponents, how can that help us solve exponential equations? And what's some real world applications for exponential functions? Go to page 2. So this first paragraph up here is talking about what is an exponential function. We just reviewed this on our notes, but they're using the same thing. F of x equals 3 to the x. And they're doing g of x equals x to the third. So they're saying 3 to the x is an exponential function. X to the third is not. Why not? So we talked about x to the third does have an exponent, but is not classified as an exponential function because the variable is in the base of the expression. The base is the variable. The variable must be in the exponent to be an exponential. Okay. Creating exponential functions. So we're going to talk about how, there may be times in your educational or your professional career where you're faced with some numbers, some raw data. Your professor or your boss will say, hey, what do you make of this? You may be tempted to say, I can make an origami swan, but don't do that. Fight that instinct. They want to know what you can understand from the data you're seeing. So let's start off, and we'll make this little table ourselves on our notes here. So if we have this table where we've got x and we've got f of x, and x is 1, 2, 3, 4. And f of x is 2, 4, 8, 16. Right? So it's a common table. We see tables all the time in math. We look at the x and we see that the x is going up +1 each time, right? From 2 to 3 is +1, 3 to 4 is +1. So this, looking at this, like, okay, this is going up 1 each time. That helps because it'll tell us a lot about this side. Is this linear? Does it go up by the same amount each time? Because when we look over here, this goes up +2. This goes up +2. Oh, it doesn't go up +2. It goes up +4. This goes up +8. Okay, this is not linear. If this was linear, it would go up 2, go up 2, go up 2, go up 2, whatever. It'd be the same number. It's not the same number. But if we look at it a different way, say, well, actually, even though it doesn't go up 2 each time, let me see. I'm going to get an ink pen just so we have a different color on the screen. This goes up times 2, times 2, times 2. That's not really a different color. It looks like it's a black ink pen. So this is going up times 2 each time, right? Instead of plus, we can go times. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So since this is going up times 2 every time, this tells us this is an exponential function, and the function is 2 to the x power. It's times 2, so 2 is the base. 2 is the base because it's going up times 2 each time. And we can check to see, is that true? Well, let's see. If it's 2 to the x, so when x is 1, so f of 1, that would be 2 to the first power. If x is 1, then this should equal what our table shows. 2 to the first power is just 2. Well, when x is 1, our table is 2. That works. All right, how about when f is 2? So that would be 2 to the second power, since x is now a 2. 2 squared, 2 times 2 is 4. So when f is 2, f of x is 4. And we do see that on our table. When x is 2, f of x is 4. How about when it's 3, f of 3? So we got 2 to the third power, which is 2 times 2 times 2. So that's 8 to the third power. Yes, when x is 3, f of x is 8. So the last one was when 4, 2 times 2 times 2 times 2, because that's 2 to the fourth. 4 times 4, 16, which is exactly what our table shows. So that kind of verifies what we thought, that this is a table that represents this exponential function, f of x equals 2 to the x. So that's what they're showing here at the bottom of page 2, is that if we have this, we can look at it and see how much it's increasing each time, plus 2, plus 4, plus 8. If we looked at it differently, we could say, wait a minute, it's going times 2, 2 times 2. And so that must be 2 to the x. And then when we check x equals 1, 2, 3, and 4, we do find out it equals 2, 4, 8, 16, just like the table represented. So that just verifies what we thought was, this is f of x equals 2 to the x. So you have all of that here on page 2 as well. If you didn't get it in my notes, or you just want to see how they do it, you can copy down notes off of the page. All right, so we're going to talk about solving exponential equations. So we're going to do this in our notes as well, just to try to talk it through and make some sense of it. So let me cross this off here. All right, if we have 3 to the x equals 3 to the fifth power. And this problem says we want you to solve this for x. Solve for x. So what would x be? What would equal 3 to the fifth? 3 to what power would equal 3 to the fifth power? You're like, Mr. Brock, is this a trick question? No, it's not a trick question. This looks kind of obvious, Mr. Brock. Yeah, it really is obvious. This is the simplest exponential equation to solve. 3 to what power equals 3 to the fifth power? You're like, well, wouldn't x be 5? Yes. 3 to the fifth power equals 3 to the fifth power. You're like, well, duh, Mr. Brock. Of course, 3 to the fifth power equals 3 to the fifth power. But I want you to think about that. What else could x be? Could it be 2? 3 squared equals 3 to the fifth? No. Could it be 0? Could it be -1? Could it be 6? There's no other number. It is that simple. If we can get, now the hard part can be sometimes getting the bases the same. If we get the bases the same, if these are the same, these have to be the same. If these are the same, these have to be. Now, this problem could have been written differently. What if we didn't have this and it said 3 to the x equals 243? And you're like, oh my gosh, yeah, I don't know. Well, 243 is 3 to the fifth. 3 times 3 times 3 times 3 times 3 is 243. So if we had a problem like this, if we can recognize or figure out that 3 to the fifth is 243, we can change this to be 3 to the fifth. And now the problem gets easy. oh, what equals 3 to the fifth? 3 to the fifth. So x equals 5. When we have something that's not the same base, what we have to do is try to get it the same base. So we had to convert that. If we convert that to a base 3, we have the same base. And then it gets real easy. Oh, well, yeah, x has to be 5 because that's the only thing that's going to equal 3 to the fifth. And that's what they're talking about right here at the beginning of this page. If you had 3 to the x equals 3 to the fifth, what would x have to be for them to be equal? Well, x would have to be 5. But instead, if we had 3 to the x equals 243, it's not quite so obvious. This is pretty obvious. 3 to the x equals 3 to the fifth. Well, yeah, 3 to the fifth. But this isn't so obvious. So if you wrote 243 as a power with the base of 3, then it gets back to where it's obvious again. Oh, well, yeah, x has to be 5 in order for that to be equal. So the key to it all, to solve an exponential equation, rewrite the equation with equal bases. That's really the entire key to what we're trying to do in solving exponential equations today. If we can write the equation with equal bases. Now that can be the hard part sometimes. That can be the hard part. So we'll see how this goes. But if the bases are the same, then the exponents must be equal for it to be true. So before we get into these properties real quick, I want to give an example because some of you are like, oh, okay, this seems a little odd. Let me give an example, kind of a preview of what we're looking at on here. Let's say we have 2 to the x plus 1 equals 2 to the 6th. It's like, okay, now that looks a little trickier, Mr. Brock. It is and it isn't. This is still the same. They're both base 2, right? This is a 2, this is a 2. So that tells us if they're both 2s, these have to be equal to each other. X plus 1 has to equal 6. Because 2 raised to this power equals 2 raised to this power. These powers have to be the same. So all we have to do then is solve for x. X equals 5. So if we put that in there, 2 to the 5 plus 1 equals 2 to the 6th. It's like, oh, yeah, because this would be 2 to the 6th, and that would be 2 to the 6th, so they'd be equal to each other. Okay, that's just taking another step further. Solving it when we have not just a little plain x plus 1 or something like that. So that's the kind of stuff we're going to get into, is solving when it's a little more complicated than the exponents, and when these are not the same, and we have to figure out how to make them the same. How to make them the same. Okay, we're going to go through down here at the bottom. These are the product properties, and we're going to do our own notes because they make it really tricky. If we're looking at the product property, we just want to look at the product property, but they're going to throw a bunch of fractions in as exponents, which makes it real confusing. You're trying to understand the fraction and maybe not understanding the product property. So we're going to do examples that are simpler than this. This is d raised to the power of 2/5 times d raised to the power of 1/2. And I don't want us to get stuck on the fractions. So we're going to write down our own examples to illustrate these 4 properties. So let's get a new sheet of paper to do that, because we're going to use these properties from time to time, and we want to just have those notes available anytime we look at them. So let's write properties of exponents. And this is just exponents in general. It doesn't have to be exponential equations. Anytime you have an exponent. So it can be exponential. It could just be a problem with an exponent in, but we're just going to look at the properties right now. And we're going to start with the product property. The product property. Now, the product property says that if we have a number, we're gonna call it x, and it's raised to the power of m, right? So this could be any numbers. and we're multiplying it times x raised to the power of n. And we're going to do some actual number examples in here, but this is just in general. To solve this, we can take m times n. Just multiply those variables together, the exponents. Multiply those exponents together. Now let's put a practical example over here, like with real numbers. So if we have x to the third being multiplied times x to the fifth. Oh, I'm sorry. I wrote this down wrong. Let me fix this. I was stuck on this multiplication. We add those together. When I started writing this down, I realized what I did wrong. X to the m times x to the n, you can just add the exponents together. That means if we have x to the third times x to the fifth, that would be the same thing as x to the 3 plus 5, which means the answer is x to the 8th. Like, is that correct, Mr. Brock? Because you were writing the other thing. Yes, because we can check this. If we have x to the third, that's x times x times x, right? That's x to the third. And if we're multiplying that times x to the fifth, we're multiplying it times x times x times x times x times x. There's x to the fifth. So if I multiply this times this, I'm multiplying x times itself 8 times. That is x to the 8th. See, 8x's being multiplied times each other. So the product property says if we're multiplying two numbers that have exponents and they have the same base, we can just add the exponents. Okay, that's going to be useful. That's going to be useful. So let's look at the quotient property then. This is called the product property because when you multiply two things together, you get a product, right? When you add things together, you get a sum. When you subtract things, you get a difference. When you divide things, you get a quotient. So this is saying if we have x raised to the m power and we're dividing it by x to the n power, we can subtract the exponents. Just the opposite of the product property. This is when you multiply, this when you divide, which those are opposites. So it shouldn't be surprising these are opposites. So that means if we have x to the 7th divided by x to the 3rd, we can say x 7 minus 3, or this is x to the 4th. Again, let's prove that. If we have x times x times x times x times x, well, I should have made a smaller number. 7 x's multiplied by each other, that's x to the 7th, and it is divided by x to the 3rd. Let's work through this. What is x divided by x? Well, x divided by x is 1. So this becomes just a 1. We don't need the x and the x. Those are just 1s now. 1 over 1 because they're the same. What about this next one? X divided by x. These cancel each other out. They're just 1. So we have 1 times 1. These cancel each other out. They're just 1. So now we have 1 times 1 times 1 times x times x times x times x, or that is x to the 4th. On the bottom, we have 1 times 1 times 1 times 1. So that's just x to the 4th. X to the 4th over 1. So yeah, you can just subtract the exponents because every one on the bottom cancels that one on top. So x to the 7th divided by x to the 3rd is x to the 4th according to the quotient property. Okay, the next one we're going to look at is the power, also known as the power to a power property. If we have x raised to the power of m, and all of that is raised to the power of n, this is when we can multiply them together. multiply m times n when we're raising a power to a power. So again, our lesson in Buzz uses fractions for all of these numbers. And that gets a little confusing. I don't want us to get stuck on the fractions. It's easier to understand without fractions, x to the 7th by x to the 3rd instead of x to the 2/3 divided by x to the 1/2 or something. We're not trying to do something real confusing. But you can look at those in Buzz if you want to. They just understand that they work the same way. They're just doing it with fractions. All right, so in this case, if we're going to do an example, if we have x to the 3rd and it's squared, look, I went smaller numbers instead of doing the 7th and stuff down the line. That means we can just multiply 3 times 2, and this is x to the 6th. Again, let's prove this works. X to the 3rd squared. So this is x times x times x. That's x to the 3rd. Now, if we square it, remember what happens when you square something, you multiply it by itself, which means we're going to multiply it by x times x times x. We're multiplying it times itself. So what do we have? X times x times x times x times x. We have x to the 6th. We have x being multiplied by itself 6 times. So the power property works real nicely. The last thing we need to know is how do we deal when we have a negative exponent? What does it mean when you have a negative exponent? Because sometimes you're going to see negative exponents. Like you're going to have x to the negative m power. I'm going to clean up this n a little bit. I'm trying to write legibly this morning. Those of you who had me last semester, sometimes Mr. Brock's writing gets a little sloppy. It's been that way ever since I had cancer. Chemo made me real jittery, but it's mostly gone, but not always. If we want this to be positive, because in our final answer, we never want negative exponents. X to the m is the same thing as 1, I'm sorry, x to the negative m is the same thing as 1 over x to the positive m. We can make it positive by moving it into the denominator. Now, the way this is always over 1. It's really a fraction all the time. All numbers are fractions. 1, 2, 3 is actually 1 over 1, 2 over 1, 3 over 1. But if it's over 1, we don't write it, right? That's why we said this is just x to the 4th. Yeah, it's over 1, but we never write if something's over 1. Divided by 1 doesn't change anything. But when we have a negative exponent, we want to make it a positive exponent. Likewise, if we had 1 over x to the negative n power, we could change that to x to the positive n by moving it on top of the fraction over 1, which is just x to the n. Right? And like, okay, well, let's look at this with some actual numbers here. So if we had x to the negative 3 power, that's the same thing as 1 over x third. Well, let's actually make that a number. Let's say, what if we had 2 to the negative 3 power? That's the same thing as 1 over 2 to the 3rd power. What is 1 over 2 to the 3rd power? 2 times 2 times 2, that's 1/8. 2 to the negative 3 power is 1/8 because of this property of exponents. You're like, well, how do we know that's true? Well, let's pull out a calculator then. Let's say, okay, if you're saying that's true, let's see what the calculator says. 2 raised to the power of negative 3. So there's 2 raised to the power of negative 3. It says it is 0.125. Well, what is 1/8 as a decimal? Well, you take 1 divided by 8 as a decimal. It's also 0.125. So 2 to the negative 3 power does equal 1/8. If you try to figure out how did you get that, it's because of the negative exponent property. Thus, 2 to the negative 3 is actually the same as 1 over 2 to the positive 3, which is 1/8. So we can see that when punching our calculator that does work. This is true. Anytime, and a lot of times you may see something in practical math where it'll have like 2x to the negative 2 power over 3y to the negative 4th power, and they'll say simplify this. And to simplify this, the only thing you can do is make these positive. So this becomes 2y to the 4th, because we took this negative exponent and moved it on top, over 3x squared. These are the same thing, but this is negative exponents. To make these exponents positive, we just had to trade places. This had to go below, this had to go above. So these are the properties we are going to be using when solving exponential equations. These properties will all help us. This all comes into play. It's all exactly what we're going to be dealing with and working through this. All right. I'm going to go back to our other sheet for notes, and these we'll have handy so we can use them as we need to. But let's go back to our lesson and see what they're going to talk about next. But those are those 4 properties. So they're down here. But again, like I said, they're doing it with a fraction. Z to the 3rd raised to the 1/5 power. It works the same. It's still the same property. You multiply those together, 3 times 1/5, and you get 3/5. I just didn't think it was necessary to put fractions in there when we're trying to make sure we understand the property first. All right. Now we get into actually solving some. Now this is a lot trickier. So this is our first example we're going to write down that is from our lesson. Let's see if we can figure out what's going on. All right. So on my notes page, I have this problem written down. 1 over 256 equals 16 raised to the power of x minus 9. Like, okay, Mr. Brock, now we're getting into something. This is a lot different than 3x, 3 to the x equals 3 to the 5th. Yes, it is. But again, the same principle applies that if we can get these bases to be the same, then it's this easy. This exponent has to equal this exponent if we can get the bases the same. So when we look at this, we have to figure out how can I get the same base? Well, this is obviously dealing with the negative exponent thing we're talking about because we're underneath there. So somehow this is a negative exponent because we're dealing with a fraction on this side. But 256 and 16, what do they have in common? I mean, we can make them both base 2 if we want to, right? Because 16 is 2 to the 4th power. We saw that up here, 2 to the 4th power, 16. We could keep going and we'll get to 256. It's a power 2. But we don't have to take it down that small because there's something else they have in common. And if we need our calculator to understand that, we could do that. Let's start doing some dividing. So 256. 256 divided by, let's divide it by 16. Oh, it is 16. So 16 times 16 is 256. So that tells us that 1 over 16 squared is the same as 1 over 256. Because 16 times 16 is 256. And it still equals 16x minus 9. Well, that gets us closer. That gets us a lot closer because now we have a common number. Now, this is not this yet. This is not base 16 yet, but we know, according to our negative exponent property, that if we have 1 over a positive exponent, we can rewrite it as a negative exponent. This is the same as 16 to the negative 2 power equals 16 to the x minus 9 power. Can you see how we got there? I haven't done anything on the right side. All I've done is rewritten the left side. I figured out that 256 is the same as 16 squared. So I rewrote it as 16 squared. Then I said, well, I need to get base 16 because that's what I have on the right side. So since I have a 16 here, if I move this on top of the fraction, all I have to do is change this to a negative exponent because that negative exponent property says these are the same thing. 16 to the negative 2 power is the same as 1 over 16 to the positive 2 power. Now I have exactly what I was trying to get. I've got base 16 on both sides. So if these are the same, I'll just get rid of them and just use the exponents. Negative 2 equals x minus 9. Since these are the same, these have to be the same. For it to be equal, everything has to be the same. So if this is the same as this, let's just solve for x. Add 9. Add 9. 7 equals x. Boy, it looks good. Let's check it. Let's check it. Let's go down here and say 1 over 256 equals 16, 7 minus 9. Right? I'm just taking that 7 that I said it was, and I'm putting it in for the x. So 1 over 256 equals 16, 7 minus 9 to the negative 2 power. Oh, wait a minute. We're getting somewhere. So 16 to the negative 2 power is the same as 1 over 16 to the positive 2 power. 1 over 16 to the positive 2 power. And we already saw that this is 16 squared is 256. So it checks. This side does equal that side if x equals 7. So there's how we solved it. We had to get these bases the same. And this one was a little tricky because we're dealing with one of these negative exponent rules. Negative exponent rules. But not too bad. Could be worse. We'll see some that are worse. Let's look at the video because the video is going to solve this differently. The video is going to solve this differently. And let me tell you what the video is going to do. The video is going to say, okay, 1 over 256 is 16 to the x minus 9. And they're going to say, this is a power of 4 and this is a power of 4. So they're going to say this is 1 over 4. Let's see, 256 is what power of 4? Let's put in our calculator just to double check. 4 times 4 is 16 times 4. So this is x to the 4 to the third times 4. Okay, so it took 4 fours to get 256. So this is the same as 1 over 4 to the fourth power. And they're going to say 16 is 4 squared. And 4 squared is being taken to the power of x minus 9. And they're going to work to get both of these base 4. Which is fine. Just simpler, since this is 256 is a base 16 number, I didn't see the need to break it down farther. But go to do this, and doing this, now they have to use the power to a power property. They got to multiply 2 times x minus 9. But I'll let you see that in this video. And even though they do this differently, they're still going to get the same answer. Because it still has to be the same answer. That doesn't change what our original problem is. So we'll watch how they do this, just so you can see a different way to solve the exact same problem.
First, create equal bases. Before solving for the variable, the bases of each exponential expression in the equation must be identical. Rewrite the numbers 256 and 16 with a base of 4 and exponents 4 and 2, respectively. According to the properties of exponents, when the denominator of a fraction contains an exponent, such as 1 over 4 to the fourth power, you can rewrite the expression with a negative exponent. On the right side of the equal sign, there is a power raised to a power. By the power of a power property, these exponents will be multiplied. Be sure to distribute. Now, solve for the variable. Once the bases are identical, eliminate both bases and find the value of the variable. Now, check your work. Substitute the value of the variable into the original equation to confirm the solution. The solution x equals 7 is correct.
All right, so you can see they ended up with x equals 7 just like we did, but they took it another step by breaking it down to powers of 4 instead of leaving it as a 16. You could do it either way. We could take it down to the powers of 2 because they're both 2 to a power, but whichever way you see, whichever way you feel comfortable with, either way, you should still get x equals 7. But that is how they got to that part. Example 2, we will work example 2 because this goes into another principle that we learned last semester. And let me write this down, then I'll switch over for this. Okay, here's the problem they gave us next. The square root of 11 raised to the power of 12x equals 121 raised to the power of x plus 1. I mean, it went a lot. X plus 1. Well, if we look at this, we said, okay, well, apparently the power we need to get to is 11 because this is a power of 11. This is 11 squared. 11 squared is 121. If you don't know that multiplication table right off, I'll help you out. So this, first off, goes back to when we looked at our unit on radicals. And we said, let me just put it in general. If we have x to the fourth, the third root of x to the fourth, we studied how we can convert that to an exponent. This is a radical. We need it to be an exponent. This we need to be an exponent because we're dealing with exponents up here. We can use our properties of exponents if we can turn this into an exponent. So what we learned was if something is inside here with the x, that would be the top of our exponent, and our exponent's going to be a fraction. Anytime you have this radical, your exponent's going to be a fraction. And what's inside with the x stays on top. What's outside right here goes on the bottom. So the third root of x to the fourth is the same thing as x to the 4/3. Like I say, this is going back to our radical and exponent unit that we did last semester. X to the 4/3. So if you don't remember that or anything, put this in your notes on how to switch back and forth because you will need that on some of these problems. Like this problem, we need that. So let's look at this problem and see what would this be. Well, this would be whatever the base is the base. So this would be 11 to some power. What power is 11 being raised to? Well, this is just to the first power since there's no number, so 1 is going to be on top of our fraction. And what number is this? Well, when we don't put a number, remember, that's just, if you just write this, the number is assumed to be a 2. It's a square root. It's a square root. So the square root of 11 is the same as 11 to the 1/2 power. These are the same, going back to our exponent and radical unit. So if you remember that, when you see the square root of something, it's just that number to the 1/2 power. And this will be most commonly what they will do in this unit is they'll use square root. So just change that to 11 to the 1/2 power. This is the same thing. And it's being taken to the power of 12x. On the right side, we can change this to base 11 because 121 is 11 squared. And it's being taken to the power of x plus 1. Okay, get something we can work with now because now we can use the power property, the power of a power. If we have a power taken to a power, we just multiply those two together. So we can just multiply these together. So this is 11 to the 1/2 times 12x. That one's not too hard because that would just be 6x, right? That's half of 12. So this is 11 raised to the power of 6x. On the right, we've got 11, and we have to multiply these together. 2 times x plus 1. We have to distribute, so that's 2x plus 2. 2 times x plus 1, 2x plus 2. So the right side is 2x plus 2. Great. We've got the same base, so we can get rid of the bases and just set the exponents equal to each other. 6x equal 2x plus 2. That's our whole goal, to get the same base. Because once it's the same base, if these are the same, these have to be the same, or they're not equal. Subtract 2x. 4x equals 2. Divide by 4. X equals 2 over 4, which simplifies to 1/2. So there's our answer. X equals 1/2. It's the checking it where it's no fun, right? Oh my gosh, let's see. Square root of 11 raised to the power of 12 times 1/2. This is our check. See if we're right. 12 times 1/2 because it's 12x equals 121 to the 1/2 plus 1. So substituting our solution in for x in our original equation. So this is the square root of 11 to the 6th power, because 12 times 1/2 is 6. Over here, this is 121 to the 1/2 plus 1 is 3/2 power. This might be easiest to check just with our calculator rather than having to go through all of the different rules again. So let's put our calculator back up on the screen. And let's take, I'm going to put parentheses 11, the square root. So there's the square root of 11. And I'm going to take that to the 6th power. Raised to the 6th power equals. Okay, so this side equals 1,331. What does 121 to the 3/2 power equal? 121 raised to the power of, and I'll put it in parentheses, 3 divided by 2. So 121 to the 1.5 power. Oh, that also equals 1331. So our solution is correct when we say x equals 1/2 because we checked it using our calculator and got there. So that's pretty tricky. That's pretty tricky. That may be about as tricky as it gets because we're dealing with power to a power and using transferring from a radical to an exponent. So we get a square root in there, all kinds of a mess. So they gave us a pretty tough example here. So they did the same thing, create equal bases. So they changed the square root of 11 to 11 to the 1/2 power to the power of 12x, which breaks down to 6x. On the right, They took 11 squared to replace the 121, and they got the same thing that we got. Their next step is just to set those equal to each other, get rid of the bases. They got x equals 1/2, and then they checked it. Oh, they checked it the same way we did. We got to that part, they just said, let's just put it in the calculator. It is equal. All right, that gets us through page 4. Let's look at 5. Time is ticking on here. Applications. Okay, well, I want to open up the chat on this as well. Suppose you were to find a bottle with a genie inside who's going to grant you a wish. One of 2 wishes. He gives you a choice. He says, I will give you $100 every day for the next 30 days. Or I'll give you a penny today and I will double it every day for the next 30 days. Oh, what are you going to choose? He says, you have to choose. Can't change your mind later. You can't think it over. Tell me, what do you want? Do you want a penny? Tomorrow I'll give you 2 cents. The next day I'll give you 4 cents. The next day I'll give you 8 cents. Hey, on day 5, you're going to get 16 cents. Then you're going to get 32 cents. Or I'll give you $100 today. I'll give you $100 the next day. I'll give you $100 a day after that. I'll give you 100, and every day you get $100. So put in the chat, which one do you want? You want $100? You want a penny? The $100 he's not going to double, but he'll give you that. So you'll have like $3,000 at the end of 30 days. All right. I'm not seeing anybody that wants $3,000. Everybody wants the penny. It says, just double it for me, sir. Anybody else? That's not many people. The rest of y'all asleep? You got to wake up. Class time, folks. We got like 9 people. That means like 10 of you haven't said it. All right, let's talk about it. $100 every day. Yeah, you'll have $3,000. Boy, think of what you could do with $3,000 30 days from now. $100 a day, you can go get you some steaks every day or something like that. Let's look at the penny. If you get a penny, you're not going to get $100 until day 15. Day 15 is the first day you're going to get $100. But look at day 20. Day 20, you're getting $5,000. That's already more than what this person was getting in just one day. Plus, you've already gotten all these other money ahead of time. Day 30, you're going to get 5 million plus, which if you add all the days together, you receive a total of $10,737,418.24. All from starting out with a penny. I mean, look at this. I mean, you don't even have a dollar. After 6 days, you haven't even got a dollar. You've got 48, 56, 60. You got 63 cents after day 6. Well, your other buddies over there were $600 and they're going, ha ha, I got $600 and you don't even have a dollar yet. But they're not laughing by the time you get up here in the teens, because suddenly you've got a lot more money and great shape at the end. So this is an exponential growth function. So let's talk about how you would write that. How would you write that? So the amount you would have would start with a penny. We'll put 0.1. That's 1 penny. And it's going to double every day for the amount of days. So if you don't know how much you have on day 20, you just make that a 20. Take a penny times 2 to the 20th power. And that'll give you your total amount. So at the end of the month, 0.01, 2 to the 30th power. This will tell you how much you have at day 30 total for every day. 0.01 times 2 to the 30th power. There's that $10 million you'd have on day 30. So if you want to know, This is a good formula to know because let's just write it like this: amount equals your starting principal times your rate times time. This is a very simple calculation that if we had, like, let's say this, and I know you have a problem like this in our assignment this week. If you have bacteria that doubles every hour, well, let's say every day. Say every day, this bacteria is going to double every day, and you want to know how much bacteria. If you start with 4 bacteria, start. You have 4 bacteria in this petri dish, and it doubles every day. And you want to know after 2 weeks how much bacteria would you expect to have? Well, we can take this formula. What would the amount be when we start with 4? It doubles after 14 days. So if we want to put those pieces together and see how that fit into our formula, doubles is this 2. 2 weeks is the 14, and that's the starting amount. So from this word problem, a bacteria doubles every day. You start with 4. How much do you have after 2 weeks? We can put the pieces together and create this formula. So let's pull up our calculator again and see what that equals then. How much bacteria we're going to have. So we have 4 times 2 to the 14th power. 2 raised to the 14th power. So we've got a lot of bacteria. 65,536 bacteria after 2 weeks. Starting with 4, after 2 weeks, it doubles every day. You got a lot of bacteria growing. So that's the type of problems you'll see that involve this type of calculation. Bacteria doubles every day. Oh, there's the graph of the penny. See, for the first 10 days, you're not getting very much. But after 10 days, when you get up 15 and 20, it's going up really fast to where you'll be up at 5 million by day 30. Okay, so this is talking about a lot of applications of exponential growth functions. Like this is used actually in real life. Let me write down this formula that you use to calculate money because that's what we're interested in. Hey, Mr. Brock, if this exponential function thing works, let's talk about cashola. All right, I'm going to put up our notes because we're going to write this down. So, when dealing with money, we use a formula that works like this. A equals P 1 plus R over N T. Now let's talk about what are the numbers we're going to use. The amount will be the total amount of money you have. A equals amount. P is your starting principal. And I'm not talking about, you know, Mrs. Hayden, our principal. I'm talking about your starting amount. Well, here, we'll put it above that. Your starting amount. Your starting amount. R is the rate of return. How much interest rate are they giving you? Rate of return, rate of interest. N is number of times interest is received each year. So, like, do you get interest every month? Do you get it quarterly? Do you get it weekly? How often are they paying you interest? Like most banks would be monthly. And then T is time, generally years. So this is our formula we'll use when talking about investing money in the bank, trying to figure out how much money you'd have after a certain amount of time. And this is exponential growth. So let's talk about it. Let's say, let's do a real life type example that kind of talks about the importance of investing for your retirement. Let's say that you've got $1,000 on your 18th birthday. $1,000 on your 18th birthday. And you can invest it in a retirement account, a 401k, and a Roth IRA, something that over the years is going to average 8%. You're going to get 8% back every year on average. And you want to know if you're 18, if you retire at 58, you retire at 58. You know, how much money would I have to retire with if I don't put anything else? All right, that's the key thing. We're not adding any more money in our retirement. We're going to put this $1,000 and just leave it until we retire at 18. So we're 18 years old, and 8% historically you can actually do better than that if you have a good investment guy. But 8% is a very conservative estimate for what it could do. So we're going to use this formula to figure out. And let's see, our interest is going to be, how often would we get interest? Probably monthly. So every month we earn some money off of that, and off that $1,000, we'll earn a piece of it each month. So how much would we have? Amount equals, what's our starting principal? That's our $1,000. 1 plus, what is our rate? Our rate is 8%. Now we have to write that as a decimal for this. We don't put 8% in our problem. We put 0.08. This is 8%. 0.08. What is N? N is the number of times interest is received each year. That's monthly, so N is 12. And then N times T. 12 times for 18 to retire at 58, 40 years. So we've built our equation. 1,000, 8%, 12 times a year, 12 times a year for 40 years. Let's simplify this, then we'll get our calculator to give us our final answer. What is 1 plus 0.08 divided by 12? Well, that's what our calculator will help us out with now. Move that over here. 0.08 divided by 12. 0.08 divided by 12. And then we'll add 1 to it, plus 1. So 1.00, and then we'll put several sixes. Try to get as accurate as we can. And then we'll finally round it up to a 7. And then 12 times 40 is 480. So there's 480 months. So you get this amount of interest each month, because 8% divided by 12 months. Each month we'll get this much, and we're going to get it for 480 months. So how much can we retire with without adding anything extra? Let's see. We'll start with the 1.006667 raised to the power of 480. And then we're going to take that times 1,000. So that $1,000 is going to grow to be $24,277 and 24 cents. So if you put $1,000 away for 40 years and can make 8% growth on it, it'll turn into $24,000. That's pretty nice. $1,000 magically turned into $24,000 if you just let it sit in your retirement account. And if you keep adding more, and let's say you can put $10,000 in there, but $10,000, you got $250,000 made off of that $10,000. Very nice math. That's how this formula helps you figure out over time how much money something can earn. So this is a good formula to have. You'll need this for our assignment, for our test, and everything this unit. So I would know how to use this. If you don't have this written down, you should have that. So you know what this is, know how to use this. This should be here in our lesson. It is. Here is the formula, and it tells you what each is. T years, the interest rates are written in decimal. N, interest earned, so this gives you the equation right there. Notice that 1 is being added to the fraction r over n. That's the initial principal. It represents the initial principal and all the good stuff. So we're going to look at this video. $100, 5% per year, quarterly, so 4 times a year. How much is that worth at 2 years? So we'll see how much $100 can grow if we invest it wisely here. Okay, let's see.
If $100 is invested at an interest rate of 5% per year, compounded quarterly, how much will the investment be worth at the end of 2 years? To answer this question, first use the scenario to define each variable. The principal, P, is $100. The interest rate on the account is 5%, which is written as the decimal 5/100ths. The account is compounded quarterly, which means 4 times each year. Therefore, n is 4. The question asks you to find the account value after 2 years. So, t equals 2. Now that only one variable is left, use the order of operations to solve for that variable. When working with money, round the solution to the nearest cent, or nearest hundredths. So, after 2 years at a 5% interest rate, compounded quarterly, the initial $100 investment will be worth about $110.45.
All right, the key to that, because you're like, okay, if I earn 5% on my $100, that's $5, right? And after 2 years, I should have $10 because that's $5 and then $5. But you end up getting an extra 45 cents because you're getting interest every quarter. So after the first 3 months, they'll give you 3 months worth of your interest. And then that is going to earn interest the next 3 months. So the next 3 months, you're getting interest on your $100 plus the interest you received after 3 months. And then at 6 months, you get that piece of interest. That's added into the pot. And now you're getting interest on that interest. And so that's how you're getting extra money over just the 5%, just the $5 a year, is your interest is getting interest. And so that's why our $1,000 grew to be $24,000. When it's just making 8% a year, that'd just be $80 a year. That'd only be $320 in 40 years, or $3,000. But instead, it earned $23,000 because the interest starts earning interest as well. So, all right. There's just another. Oh, we do have another formula in there. They talk about the other thing it could be is if you get continuous interest. And you'll never get continuous interest. Let me put this up on the screen. I wrote this down. This is continuous. Now, you may have some things again where maybe on a bacteria, instead of if they have some different rate or time, maybe it's not doubling per year. We looked at the formula that we can use. It wasn't on this page, it was a different page. But at the formula we can use, if something's doubling every year, but let's say this bacteria is growing at 10% per year or per day or per month or something. This is the formula they have you use for that, because this is continuous. It's not like the bacteria stops and grows once a day. Once a day it grows. That'd be like getting your interest once a day. But bacteria is growing continuously. So this is the formula they use. And you're like, well, P is the principal, R is the rate, T is the time. What is E? Well, E is just a number. Like, what? What, Mr. Brown? Yeah, you may not remember on your calculator, but there's a button right here that says E. E is a number. It equals 2.71828182845. E is a number in math, and this is the number E. So you use the principal times E raised to the power of the rate times the time. ERT. So that is what they're looking at right down here. If you have $500 and account 6% per year compounded continuously, which means every millisecond you're getting a milliseconds worth of interest, which is not going to happen. How much is after 3 years? So they use that A equals PERT, $500. The rate is 6.06 in 3 years. So E to the power of 0.018 is equal to 1.1972, et cetera, times the 500. And it'd be worth $598 after 3 years. Again, that's used more on bacteria than money. The only other thing we need to talk about before we run out of time is exponential decay. A decay function. So a decay function, let's talk about it in terms of what we've already looked at. In this problem, our rate of return ended up 1.006667, right? Because it's growing at 0.08%. So we're growing at 8%, 12 times a year. It's growing. If, let's say we've got a car that we paid $20,000 for, and it's going down 10% per year, because cars lose money. Actually, they probably lose faster than 10%. And let's say after 5 years, and it's just once a year that we talk about the car, because as it gets a year older, now it's worth less. A year older, so our rate is annual, just annually, which means n equals 1, because it's just 1 times a year. So if we use our formula, the amount, how much is it worth? It started at 20,000. It's 1 plus negative 10, negative 0.10 over 1. So I'm not putting the 1. After 5 years, again, 5 times 1, because the n is 1. If we simplify this, 1 plus negative 10%, this is 20,000. 1 plus a negative 10 is 0.9. If you see this number is less than 1, less than 1, we call that decay. You're losing value. It's going down. You've only got 90% left each year. I've got 90% of what I started with. 90%. This, I've got more than what I started with. 1 point. So this is greater than 1. Greater than 1 is growth. I'm getting more money because this is greater than 1. If it's just 1, nothing's happening. It's not growing. It's not decaying. It's just you keep the same amount. If it's greater than 1 is grow. It's less than 1 is decay. Let's actually see what this is equal to then. Let's see what our $20,000 car depreciating at 10% per year after 5 years, which I think actually they depreciate faster. 20 times 0.9 raised to the fifth power. So that car's worth 11,000. It's probably worth about 8,000 after 5 years. But so that's our answer after 5 years. At 10% decay, it's going down in value. So that's the key. Is this number greater than 1 or less than 1? So I'm highlighting both those on our notes. Greater than 1 is growth, less than 1 is decay. After you simplify it, this, we're like, what? You know, is it growing or is it getting smaller? All right, and that's what this is talking about. Oh, here's a car going down. This one's losing 20% per year. That's probably pretty accurate. So it's 0.8. It's smaller than 1. So another decay function. It's going down 6%. This boat, let's see. Oh, it's using the E formula because it's going down continuously. So, all right, let's look at the lesson summary. The lesson summaries, each unit has lesson summary. You can print this if you have a printer and want to keep this as your notes, because this gives the compound interest formula. It gives the continuous interest formula. It talks about exponential growth, exponential decay, talking the base of that exponent greater than 1 or less than 1, between 0 and 1. How to solve exponential equations. You got to get an equal base on both sides. There are some sample problems for you here. On page 7, you can work this and it'll tell you if you're right or wrong. It'll give you the answer. This is where you try to figure out, do I know what I'm talking about? 10 to the 2a plus 3 equals 10 to the a minus 4. Hey, that's great. These already are the same base. So we can just set 2a plus 3 equal to a minus 4. Solve that. Hit submit, and it'll say, yeah, you're right. And it'll give you how it was solved. Then you can go to the next problem. This one is 6 and 36. So you need to change the 36 to base 6. Anyway, there's 5 problems. Then you can go to activity 2. And now we have the interest. $75, 8% compounded monthly after 15 years. Put that in that interest formula. Figure out which one of these it will be. I'm just going to take a guess. Oh, I just took a guess. It was right. So there's 3 of these problems. Here, I'm just going to choose one, hopefully wrong. It'll say, oops. And it tells you, remember, write the rate as a decimal. Find the time. Try again. It'll give you a second opportunity. So you can go back and try to fix what you did wrong if you did something incorrect. And guess again. And then activity 3, this is depreciating at 20%. It's going down. It was $349 when you bought it. How much has gone down after 4 years? So like $142? Yes, it's gone down a lot. So anyway, there's sample problems that you can try. It'll tell you if you're right or wrong. It'll tell you how to do it if you can't get it right. Let's look at our assignment since we're running out of time here. The last page just says, make sure you read the lesson and do the assignment. So if you go back here, the assignment follows the lesson. And you get 3 attempts. So if you don't do well the first time, you get 2 more attempts. Hey, these are both base 3. So that's an easy start. This is base 3 and base 9, base 81 and 27. So I would change those both to base 3. Oh, there's one of those 1 over 36s. There's one of those square roots. So that's 6 to the 1/2. Here's interest, $240, 9% per year, monthly, 14 years. Here's one of the A equals PERT. You're using E in your calculator. By the way, there is a calculator right up here in the menu bar you can use. Here's bacteria that triples in size each week. That's it. Your rate's 3 times, right? 3. 10 problems altogether. 10 problems. 5 of them are dealing with the exponentials, solving exponentials. 5 of them are dealing with growth and decay. All right. If you're having trouble with these, we will have class. Have class on Thursday. It's not required. It's totally optional for you. You don't have to come to class Thursday. But if you're having trouble, you should try this before Thursday so you know, or I need to go get some help. And you don't have to stay the whole class. Come get some help, and then you can go finish whatever you're working on. But again, totally optional Thursday. You do not have to be here. But I will be here in class if anyone needs anything. So, all right, guys, have a great week. If I don't see you again until next week, we'll see you Tuesday. Next week, Monday's a holiday, so A Day will be moved to Wednesday. But we'll be the same on Tuesday next week.